Hello, everyone. Good morning, and thank you all for being here. Um, so today we have a series of seminars called. So I'm welcoming you here for our series of seminars. Is Physics Without Frontiers, Expanding Physics for Sudan Horizons Seminar Series. So here we are very happy to welcome Dr. Frederik Schiller as our speaker for today's seminar. And Dr. Fred, he's senior scientist at the Materials Physics Center in Spain, and he's also my supervisor. And today's seminar is a bit different than for the online participants. It's different than the two we had and the ones we will have in this month and the next month. So we will have the in person, the members of the Nanophysics lab. They are joining us. They are experts in the field of surface and catalysis. And the online participants, they are students, Sudanese students and researchers are. So for our online participants, this seminar, it brings together the expertise in surface science and catalysis to participate in a new, unique opportunity that inspires those students and researchers for the future of Sudan. So we are very excited to have you all here, the members of the Nanophysics Lab, and also the Sudanese researchers and students. I will give a brief introduction about our initiative and also the Nanophysics Lab and our speaker. So I have some slides to share. Can you see this? Maybe here. So these are the slides. So we have the initiative is Sudanese. It's a joint initiative between ICTP in Trieste, Italy, and also the Photon Center. So we have a 6-week series of seminars where we present various topics in physics, from astronomy.
Sorry for the interrupt.
Yes.
Yeah, could you please maybe the voice? Some people are asking the voice is not clear, and also try to adjust the camera to the attenders, please. It will be better.
Okay.
Yes. Hi everyone, and nice to see you all.
So those are the participants online. The 6 weeks series of seminars includes different topics from physics, cosmology, astronomy, and the aim of this initiative is actually to connect the students and researchers with skilled experts in these fields. Despite the conflict and the war now in Sudan, where all the education stops, we are trying to inspire the students and researchers to continue further the physics journey. So next is the nanophysics lab. For our participants is the group where I'm working now, and we work on we apply synthesis. In the nanophysics lab, we apply the synthesis of atomically perfect materials to practical problems of technological and industrial interest aligned with current challenges facing our society. The main research lines we are working on is the materials for quantum technologies, nuclear precision chemical sensors, and the green chemistry catalytics. And today's seminar is hosted by the Green Chemistry Meetings. So, our speaker today, Dr. Frederik Schiller, he is a staff member, a staff scientist at the Materials Physics Center. He is also a board member of the peer review committee at two synchrotrons, Soleil and Daisy. and he also holds a PhD in Natural Sciences from Technical University of Dresden, and he also obtained a diploma in physics from the same university. His research expertise are in curved crystals, catalytic reactions, and the standard microscopy, the photoemission at ambient and near-ambient pressure. He developed methods for in-situ spectroscopy. He also a farmer, Marie Curie fellow, and also Raman Tahal. He designed beamlines at Alpha Synchrotron, and he obtained 3 awards for his scientific work. Please, everyone in person and also our participants online, welcome Dr. Frederik Schiller and the stage first.
Thank you.
I think we have to stop sharing. Let's see. This goes. Do you see something now? No?
Yes. Now it's nice.
Okay, I start. So thank you, Allah, very much for the introduction, and welcome to this seminar series. I hope you can learn something out of this all. So today, as Allah said, my name is Frederik Schiller, so I'm working in the Spanish Research Council in San Sebastián. And so, as Allah already introduced, this is the Nanophysics Lab, and I'm a member here as a Green Chemistry Group member.
Yes.
Prof?
Good. I think.
So, you see, or hopefully you see, so there's Sudan. We are there in Southern Europe. So if you want to come walking to us, it will take you a lot of time. So nearly half a year. So it's better if you want to come to take the airplane. But more or less now you see a little bit where we are situated. If you come back, you see we are on the Atlantic Ocean, just in the northern Spain, close to the border to France. Good. I mean, I will skip a little bit the history of our institute. So we're starting 2003, and since then we are quite a lot of people. So this photo is already now, I would say, 3-4 years old, and you see we are now around 15 people. So in more or less 3 subdivisions, and very importantly, here you see Allah in the foreground, who is actually responsible in part that you can listen to these seminars today.
Can you hear me, Prof? Sorry.
Good. So what we are doing here, so basically we are experimentalists. We have our labs. In these labs, we are doing basically everything that's related to surface science. So if you have a look to all these machines, to all these equipments, you see something basic in common. This is everything, let's say, vacuum machines. So basically on a surface, what you try to do, you try to work with electrons, because electrons are very sensitive to surfaces, and electrons does not survive in air a lot. So basically you have to make vacuum, and that's why all our techniques that we have around are based in vacuum. So there are 2 main things what we are doing. One is scanning tunneling microscopy. You see this is the shortage of this STM, so we have several equipments. Here in the university, we are actually now, and also in our institute, is just on the other side of the street. And this STM, together with low energy electron diffraction, actually allows us to learn something about the structure at surfaces. And the other part of the experiments that we are carrying out is photoemission techniques. So you see here XPS or UPS, so X-ray photoelectron spectroscopy or ultraviolet photoelectron spectroscopy. So this is some spectroscopy technique. How to do that?
I think
better?
yes, now perfect.
Let's see how to do that. Okay. Now I go out of that. This one. That's good.
Yes, and now you can just make full
Now.
presentation.
Before it worked so nicely, and now we changed something.
Can you hear me, Prof?
Tengo que coger una de esas.
I think you need to talk with Allah about the voice. They can't hear us.
Because in the chair. Okay, so sorry, I go back to where we were, hopefully. Not sure how to remove the one on top, I'm sorry. Okay, good. So again, basically, we have all these techniques here around, but for the talk today, I will not speak about what we are doing here in our home lab, but I will speak about what we do somewhere else. Somewhere else, that means when we need, or when it's really necessary, we go to large-scale facilities. In this sense, these are synchrotron radiation facilities. They are all here marked in this map of Europe, so there are several around. Out of Europe, there are the USA, in Brazil, they have some, in Canada, in Japan, in China. Sadly, there's no one in Africa. I think there's a project to build one in South Africa, but I mean, this is still a very long time to go. So for the moment, the idea is basically like that. So in a synchrotron, you have some electrons. Electrons are going in some vacuum system. They're going here around. You see this? Let me change this to this guy here. So electrons, I see two now. So basically you watch to the right-hand one, not to the left-hand one. So the electrons are going around here. Let me check if I can remove it. Okay, so basically the electrons are here going around, and electrons are usually going straight until you put a magnetic field or some electric field, and then the electrons, they are a little bit going to the side. So for example, here on this, they are going to the side. But when they are going to the side, then you get some radiation in the direction where this electron was going to. And now one can use this radiation. One can, let's say, select certain radiation out of that. And this is what we call a beamline. So, and then in this beamline, you can use a part of this radiation. For example, you're interested, let's say, in a certain X-ray diffraction, then you need a high photon energy. you want to do some photoemission, as I will speak today, then you need a lower photon energy and so on. So you see here around, there are several. We have one in Spain, there are several in Germany. So the ones I will speak today about is here from Daisy, from Hamburg, northern Germany. And some experiments are done at Max 4. This is in southern Sweden, in Lund University. But this is actually like such a building looks like. So we have the top view from Google. And you see here there are some streets crossing, so you have an idea about the dimensions. So more or less the diameter of this building is around 150 to 200 meters, a little bit depending on the synchrotron that we are talking about. This one is actually the synchrotron of Berlin. So Berlin is here. Now, the one we are talking about will be these two, but then just to see the dimensions. Now here, for example, you have a car, you have another car. So these are very big buildings. So this ring that I have told you before is close to the inner part here, and then the electron that's are coming, the light, sorry, that's are coming out goes to these beam lines there in the outer part. So if you have a look inside, then it's basically what you see. We are here, let's say, on this wall section. So all this ring is behind this wall, and then you have tiny openings. You see here where this light is coming out. And such an opening is actually here, for example. There are some fences because you have this radiation. You have to protect people from the strong radiation. And there are some optical parts here. These optical parts actually cut out things that is not necessary, remove radiation that we do not want. We need a monochromator to select the photon energy and so on. And then all the thing is traveling around these metal tubes to the experimental station. Since we do not see here the experimental station, we come to the foreground. Again, so the light from another beam line close by comes out here, wall behind these cables, and go here inside of this experimental chamber. And if you focus even further, you see, comes here in, the light, and here now we have our experimental station where we will carry out our experiments. Then you see here's Alain. He is actually moving some samples around in this chamber. So, outline of the talk. So today I want to talk about catalysis. So heterogeneous catalysis in this case, and what we can do with photoemission in this thing. Then in the second part, I want to show some examples, what we do. So we are doing two reactions I will show you, where some very easy one. One is the oxidation of CO to CO2, and the other one is the reduction of nitrogen oxide. What is catalysis? So catalysis, most of you have heard about it, probably even in high school. So in my case, I learned in high school just the Haber-Bosch process. And what is a catalyst? So a catalyst, defined by Ostwald, some German chemist, some little bit more than 100 years ago, said a catalyst is a substance which affects the rate of a chemical reaction without being part of its end products. It means a catalyst accelerates a reaction, it lowers the energy, it gives a better sensitivity to a certain reaction that we want, and so on. So this is basically the definition that he put. So coming back to this Bosch-Haber process, the one that I learned in high school. So basically, this is a process that combines nitrogen, hydrogen to ammonia. This is a very, very important reaction because this made us, let's say, the humanity to grow from this, let's say, 1,000 millions of people, inhabitants of the Earth in more or less 100 years ago. Now we are around 8 million. So I mean, basically this is the reaction. So this ammonia is part of fertilizers, and these fertilizers are used in agriculture and in other areas. And nowadays, basically 50% of the nitrogen that we have in our human body is actually arising from artificially produced nitrogen through this Haber-Bosch process. So this is really a huge and very important catalytic reaction. So here you see some of this industrial process, where industrial, let's say, area where this takes place. You see it's a huge area with a lot of things. And this lot of things that you see here around is basically for the reaction to get the hydrogen. Now, hydrogen is produced out of natural gas nowadays. And so basically natural gas, you have methane, CH4, and then you have to split this CH4 into hydrogen that we want to use later on for this process. And also here we have some different catalysts inside, but I mean, all this, just imagine that you can do to produce this hydrogen somewhere else. So you in Sudan, you have a lot of resources there. All the possibility to create energy with solar cells, you can use this energy to produce hydrogen, and then you just need the nitrogen. Hydrogen you get out of water, so you need a little bit of water, of course. But I mean, you have the nitrogen that's inside the air, and you can combine this and get a lot of this ammonia. This ammonia you can use for yourself, you can export, and it's a very important material in the future for this green ammonia, so to have, let's say, a fuel for cars, a fuel for ships, and so on. So it's a very important process. So coming back to the process itself, it's an exothermic process. So when we do this reaction, we would even gain energy. The point is that our initial, let's say, materials, nitrogen and hydrogen, they are molecules and they're difficult to break. So, and since they're difficult to break, this nitrogen triple bond that we have here around needs really high temperatures and high pressures. So you see the pressure in this reactor that is there behind is around 300 bars and the temperature around 500 degrees centigrade. And again, it's a very important thing. Now, it requires 2% of the world energy only to produce this ammonia. And it's contributing to 3% of the global CO2 emission. And again, I mean, there's a possibility a lot for African countries to do such reactions and, let's say, be able to export such things later on to increase, let's say, your economy. The catalyzer for this reaction, what I'm talking about, is actually iron or iron oxides, but it's not only iron that is used, it's also some other materials that we will see in the future. The idea behind is that, so we have this triple bond of nitrogen. It's very, very stable. That's why in our surroundings, we have a lot of nitrogen. It's not reacting too much. And it's nearly 1 megajoule per mole, this triple bond strength that we have to break. And the idea of the catalyst is depicted here. So we have to overcome this barrier to break it, and then we get to our end products. And now with this catalyst, the barrier is much reduced. So even we need this 300 bars and this 500 degrees centigrade. If we would not have the catalyst, we would even need more energy. So the idea is that the nitrogen molecule comes to our surface. So this is the iron. And when it sits on this iron, basically what we do, we make a chemical bond from the nitrogen to our iron from both sides. And this chemical bond that we create will weaken the chemical bonds between these two nitrogens. So it will weaken this triple bond. So the electrons from here go a little bit towards the iron. And then we are able to break this. We're breaking this nitrogen bond, and now our nitrogen is actually free on the surface. So we have atomic nitrogen. We have to do the same with the hydrogen. Hydrogen is not so much a problem. We end up now with all these atomic species, hydrogen and nitrogen, and we just have to bound them together. And then, let's say at the end, the ammonia can leave our surface. Again, catalysis is a very important process. It's not only the, let's say, that happens in some reactor or something like that. Also, catalysis takes place in nature. So one of the most important catalytic reaction in nature is photosynthesis. It's actually a photocatalytic process that converts the energy of the sun, the carbon dioxide that we have in our surroundings and water, and out of this, what we are doing is, let's say, organic material and oxygen. And without this photocatalytic reaction, we would not exist here. So the catalyzer that you have inside in these plants is actually chlorophyll. This is a picture of chlorophyll A. And this is responsible that we do this process. And this is responsible that we get organic material out of that. You see, it's basically a, for those of you who know a little bit chemistry, this is a porphyrin molecule with a central atom. This is magnesium in this case. And it's often like that. The catalyst has usually some, for example, magnesium iron we have seen before, what could be also some oxide of a metal, but usually it's some metal involved in there. Other biological process, for example, if we have once this glucose out of the plants, we have to transfer that in our body to energy again, and also in our body, we are not having a fire in our body, so we have also some catalyst that now converts this glucose again to energy. And also here in our body, we have certain type of catalysts that also contain magnesium, or some other plants, they can have iron, something like a central atom for that to make the other reaction back. Let's come back to the industry. That's a little bit more our ambient. So this is like such a catalyst in this Born Harbor process looks like. Now you see this is an electron microscope image. You see the scale here, 100 nanometers, sorry. And you see there are tiny particles here around between 5 and 10 nanometers in size, was actually this iron catalyst part. So we have a large surface here. You see the surface area of one grams of this is very little, 1 grams, is around 20 square meters. So we really distribute all the things a lot. You have some structural support on the bottom, so some oxides, aluminium oxide, calcium oxide on promoters, not so critical. And again, this was discovered and this is in use since now around 110 years. So, and if you have a look, you see everything is in the nanometer scale. So there was already nanotechnology 110 years ago. So now we are very proud that we investigate in nanotechnology, but this was around for a very long time. So how we can study that? So already Langmuir, famous British scientist, told some in 1930, so also nearly 100 years ago, that the most finely divided catalysts, or something like we see here, must have structures of great complexity. So he hasn't seen that in his life, this picture, because this was quite new. In order to simplify our theoretical considerations, so he was a theorist of reaction at surfaces, let us confine our attention to reaction on plane surfaces. If the principle in this case are well understood, then we will understand later on what happens in, let's say, in catalysts of more complicated structure. And he said that in 1930, and it took, let's say, scientists around to 1960, 1970 to start with such investigations, to have the ability to make such pictures in starting surfaces. And this is a little bit what we will do today. So this is the subject I want to show you. So this is this heterogeneous catalysis. Uncurved crystals, we will see what it is. So we are a little bit going away from this ammonia. We are going now to this CO oxidation. And a little bit the first point why it's important, this CO oxidation. So let's say a lot of our mobility that we have around nowadays depends on cars, depends on airplanes, on ships, train. And what we do there, we burn some hydrocarbons that we have from natural oil, from natural gas, and so on. We combine this with oxygen, and the idea that we get out our energy that we need. And we have, of course, byproducts, CO2 and water that are generated. But I mean, we have other byproducts that we do not want to have. So in this, in the gas oil, in the gasoline and so on, we have also some tiny part of nitrogen, and this nitrogen oxidizes to nitrogen oxides, different NOx. We also will generate some CO if we have an incomplete combustion. Some of these carbon nitrides is not completely burned. So in general, we have a lot of pollutants, and this pollutants, let's say, is quite bad for our environment. It's quite bad for us because we are, let's say, breathing these pollutants then every day. So then since a lot of years now, more or less 30 years, so cars at least, and also some of these, let's say, ships, they have now catalyzer inside that try to clean these exhaust gases that we have. So one of the reactions that we have to address is the CO oxidation. So to combine CO with some oxygen to make CO2, because CO is a dangerous gas. Again, we have to burn a little bit some hydrocarbon that were not completely burned, and we have to reduce this NOx to nitrogen and oxygen. And this is like actually how it looks like. So on the lower part of the car, you have nowadays this three-way catalyzers, and this is like it looks from inside. So it's again some very porous materials, as we have seen before in the case of the Born Haber process. And there on top, we have these tiny parts, these nanoparticles of the catalyzer. In this case, it's some platinum-like materials, the platinum, palladium, rhodium, or iridium, some materials that belongs to this platinum materials. The idea for this reaction, so basically again, we combine the carbon monoxide with oxygen to build the carbon dioxide, is to get both of these materials onto our catalyzer. So this, for example, could be some platinum, or this now rhodium. The carbon monoxide stays on our surface, and the oxygen goes to the surface. We dissociate them, and then one oxygen goes, let's say, to this carbon monoxide, the other side to that. We combine them together, and they leave the surface as carbon dioxide. And now the surface is again ready to the initial process to, let's say, to get again, to convert more of these CO and oxygen to this CO2. This reaction is known since a long time. And a catalyst looks then like that, for example, here. So this is some catalyst that was, let me see, can make the video. Yeah. Up. So a catalyst may work in the sense like that. You see now this video or not? No. Let's see if it somehow is able to work. No, I'm sorry, it doesn't work. Anyways, I mean, catalysts that you have here, you see it has parts that are working. So for example, this is now ready, that this reaction takes place, and it can have parts where this is not ready because it's completely full. Now you can imagine if it's completely full of carbon monoxide, so we cannot split the carbon, the oxygen. And then in the video, basically what you see, like these fronts, they're actually then moving. I'm sorry, it doesn't work. Okay. So basically, again, on the bottom of the car, we have this catalyzer, the gases comes in, and when we have a look to the inner part here, we have seen before this was this porous material, and on top of this porous material, we have this nano-sized particles of this catalyzers, so platinum, rhodium, palladium, iridium, some of these materials. And when we have a closer look to them, they look like that you see here. Now, this is one of these materials. We see we have some facets, we have some side facets on the end here on this and on the top, but we also have, let's say, steps between them. We have corner atoms, and all of these atoms, they have a different neighborhood. And now the question is, what is responsible now for this CO oxidation? Is it, let's say, the phase here, if it's this corner, if it's the corner atoms here, if it's the step there, and this is what we want to study. So there are already some theory that will help us to do such things. For example, here we see this is a calculation some years ago, where we actually show one nanoparticle here, and basically the color scale that we have here is the adsorption energy of the CO. Again, we have to have the CO stick to the surface, if not, we cannot do the reaction. And then you see, already on the color scale, you see that we have a certain adsorption energy here on this middle of the terraces, so minus 1.4. If we have another terrace, so this is, let's say, a 111 surface, this would be a 100 surface, then you see in the middle of the terrace, we have another energy for this CO adsorption, so basically we are here. And if we go, for example, to this corner atoms over here, then you see CO would stick very strongly to this corner atoms and would be bonded quite a lot. So now we can make such a calculation, but this will not help us yet to know where actually our process will happen, our CO oxidation. So what we do then, where we are expert in our labs, we take a single crystal that you have here. We have a very nice atomic order of our atoms. So everything in place. So for example, this is a 111 surface. And what we do, we curve that crystal. So we polish this single crystal in a certain way that you see over here, that we have in the middle, still the same, but then when we go from this middle to one of these sides, then we introduce steps. So we cannot cut, let's say, an atom by half, so we have a step and so on. And when we go from, let's say, this middle, we have in this case a 111 surface, we go further and further and further, then you see here at this side, basically you have then step, 2, 3 atoms, and another step. And again, the reaction is like that. We have to have the two materials at the surface. So basically, on one hand side, we have our CO sticking to the surface. On the other hand side, we have this oxygen. The oxygen we have to dissociate, and then we have to give. Let's say this is the process that we have to combine them, and CO2 leaves our surface. So in this animation that you see here on the bottom, this is from already now nearly 40 years old. This is from Nobel Prize winner Gerhard Ertl, who made this animation. And you see, so we have, let's say, some blue things is coming here. This is the oxygen, it dissociates. The red thing here is, let's say, the CO. They come together, combine, and CO2 is leaving the surface. So basically, on this materials, we have two stages. The first one is what we call the Poisson stage. So, or the inactive part of the catalyzer. It's when we have, let's say, iron here in our environment, the nitrogen will not split. So if we have this platinum-like material, so CO would not get oxidized here. We overcome a certain, let's say, certain barrier, energy barrier, for example, that we can overcome with temperature. So these materials, this, let's say, transition metal materials, they're very prone to get CO stick to them. So you see it here. We have, let's say, this is platinum, or this could be rhodium, and CO sticks in an environment like we have here, just to the surface, and then it occupies all surface positions. And then, of course, oxygen cannot dissociate anymore here. Everything is full. So we have no CO2 production. If we go to the active part, so we increase the temperature. Increasing temperature means that we are, let's say, moving these atoms around. It can dissolve from the surface, and now we have space. Oxygen can split on the surface, can dissociate, and then we can do the process here around. So the difference between that is what we call the ignition, or when we start the catalytic process. And this is what we want to, let's say, study here. So we do a first experiment. Let me see if I can move for you this thing. I'm sorry. So basically what we have here, we have this planar laser-induced fluorescence experiment. Planar laser-induced fluorescence means that we have a laser that shines light from the left or from the right, and the energy of this laser is tuned that we can create a fluorescence in CO2. So CO2 is actually the gas that we want to have. So if we see then certain CO2, we will see here a different color. So let's say if this video works today. It's also not working. You see it there below? Okay, so I mean the video should actually show you like the, let's say with different temperature, like now this sample gets activated, and then let's say we see here actually it will start on this B side, and then we have the other side. I think I have a resume here on the next slide. So sorry that the video does not work. So basically if we have a low temperature, nothing happens. And then from a certain temperature on, in this case 530 K around, we see that we illuminate this side. So here we are producing now CO2. And then a little bit later on, so around 5 degrees later, so the A side gets active, and finally also this 111 in the middle. So we have some asymmetric process. So asymmetric CO2 production. We have some pre-ignition that happens first on this B side, and so on. So we know now a B side, so a stepped surface with B-type steps is much nicer than having a flat crystal, but we do not know what happens. And then we come to the point that we can now study with our methods why this actually happens. And this is where this photoemission spectroscopy comes in. So we have our photoemission spectrometer, photoemission basis on the photoelectric effect, first seen by Heinrich Hertz and then later on by Albert Einstein in 1905. So he got actually also the Nobel Prize for that. Heinrich Hertz didn't get it, very bad. But it took them another, let's say, 60 years to really use this photoelectron process in this, what it was first called ESCA techniques, electron spectroscopy for chemical analysis. And the idea behind this invention from Kai Siegborn was that the electrons that are coming out when we shine some light to a sample, so the electrons that are kicked out, they have a certain energy that is actually for each element different. So here we see one spectra that we took here in our lab. So this you see, it's a gold 111 crystal, and basically this is what we measure then inside of our electron analyzer. So we have, let's say, different levels, so inner levels, so the 4F, for example, of the gold, 4D, 4P, and so on. And if we would not have gold, if we would have platinum, for example, so all these lines, they shift a little bit left-right. And then we can actually, if we are able to measure the Fermi energy here, then we can, let's say, address them, and we know, so for example, this is gold,